In this class, I am going to discuss about coupling schemes. Before going to this topic, let us recollect what we learned so far. So far, we learned about different atomic models. In all atomic models, the basic principle is the angular momentum of the electron when it is revolving around the nucleus in a particular orbit is quantized. In Bohr atom model, the angular momentum of the electron mvr is equal to nh by 2 pi. This is the quantization of the Bohr electron. Whereas in case of Sommerfeld model, the angular momentum is quantized such that the radial angular momentum is equal to nr into h by 2 pi and azimuthal angular momentum is equal to n phi into h by 2 pi. So, like that, the orientations in vector atom model, the orientations of the orbits are also quantized. The orientations, that means the only limited orientations are permitted. So, in that orbital quantum number which is nothing but Sommerfeld's azimuthal quantum number, that is also quantized such that the permitted orientations are always only the according to classical theory, there are number of permitted orientations, but in our vector model or according to our space quantization, only limited orientations are permitted. They are also quantized according to their angular momentum. So, but in almost all the cases, we discussed about the angular momentum of the single electron. We discussed about the angular momentum of the single electron. But in case if we consider the number of electrons in an atom, then the total angular momentum depends upon the interaction between orbital and spin angular momentum. The interaction between orbital and spin angular momenta. If we consider the number of electrons, not a single electron, then the total angular momentum, this is not the algebraic sum of the angular momentum of all individual electrons, because this angular momentum is a vector quantity. So, we have to consider the vector addition. So, the resultant angular momentum in case of number of electrons depends upon the interaction or coupling between orbital and spin angular momenta. So, in general, there are two types of interactions. In general, there are two types of couplings. One is Russell and Saunders, Ellis coupling. One is Ellis coupling, Russell and Saunders coupling. And the second one is Ellis coupling. And the second one is JJ coupling. JJ coupling. In case of Ellis coupling, as we represent in this diagram, the Ellis coupling, the resultant of all L vectors is to be taken as capital L is equal to L1 plus L2 plus L3 plus etc. and capital S is equal to S1 plus S2 plus S3 plus etc. Then the resultant is given by J is equal to L plus S. Then the sum of the angular momentum is given by J is equal to L plus S. This means the vector addition of all L vectors gives the resultant L, and similarly the vector addition of all S vectors will give the resultant of S. So then the total angular momentum can be written as J is equal to L plus S, capital L plus capital S. This is one way of the estimation of the total angular momentum of a number of electrons in an atom. In order to estimate the total angular momentum in this type, what we have to do? We have to calculate the total angular momentum and also the total spin momentum. Then only we have to add these two, which gives the resultant of the total angular momentum of an electron. So in this, the resultant of L is nothing but L1 plus S, L2 plus S2. But the resultant of S, if S is even, it is an integer. If S is odd, then the resultant of S becomes 1.5, 2.5, 3.5, etc. Like that, J is equal to, then the J is equal to L plus S. The second coupling is named as JJ coupling. In this coupling, the total angular momentum of the individual electron, we are considering the number of electrons in an atom. Say for example, there are 2 electrons in an atom. So the total angular momentum of each electron, L1 and S1, the total is J1, the resultant. Here total means the resultant is the J1. Similarly for the electron, L2 and S2, and their resultant is J2. The sum of J1 and J2 gives the resultant angular momentum of the atom. In this case, it is L plus S. Here L is J1 is equal to L1 plus S1 and J2 is equal to L2 plus S2. Then the resultant J is equal to J1 plus J2. Here we have to remember that these two values are not same because this is the vector addition. So the Ellis coupling is also called as normal coupling because in many of the cases, in almost all cases, the total angular momentum of the atom supports this coupling. In few atoms, the total angular momentum is given by this type of calculation or this type of coupling, that is JJ coupling. So Ellis coupling means the resultant of all L vectors of the electrons plus the resultant of all S vectors of the electrons. Then the resultant J is given by L plus S. In JJ coupling, we have to determine the total angular momentum of the individual electron separately. So J1 for the first electron it is L1 plus S1. Similarly for second electron it is L2 plus S2. Then the resultant is given by J is equal to J1 plus J2. This is the vector diagram which is useful for us to estimate the resultant angular momentum of the electrons in an atom. The resultant angular momentum of the electrons in an atom. So, with the help of this coupling schemes, we can easily understood the different energy states of the electron in different orbits. So this is about Ellis coupling and JJ coupling. Now I am going to explain the selection rules. Selection rules means, as we know that the cause for the emission of radiation by an atom is the transition of electron from higher energy level to lower energy level. In the case of Balmer series, we will get visible spectrum. In the case of Balmer series, we will get visible spectrum. In the visible spectrum, the spectral lines are having different intensities. So, we are going to search for the reason for different intensities of the spectral lines. And also, only limited lines are appeared in that spectrum. What is the cause? That means only limited transitions are possible. So, that means almost all possible transitions are not taking place in an atom, but they are also limited. Only selected transitions are possible. What are those selected transitions? That is we can easily follow by understanding this concept of selection rules. Whenever the electron taking transition from higher energy level to lower energy level, it suffers a change in its total L value and total J value and total S value. The resultant L value of the electron when it is in higher energy level, when it takes transition from higher energy level to lower energy level, the resultant values of L, J and S are affected, because so these transitions takes place if and only if the change in the energy levels, if and only if the change in the delta value, delta L means change in L value when the electron takes transition from higher energy level to lower energy level is equal to plus or minus 1. Delta L, the change in L value of the electron when it undergoes transition from higher energy level to lower energy level, then the only such type of transition is possible in which delta L is equal to plus or minus 1. Similarly, for J, delta J is equal to plus or minus 1 or 0, but 0 to 0 transition is not permitted. That means if the resultant of J is 0 here, if it takes transition from lower energy level, here also the resultant of J becomes 0, then that transition is not allowed. But the change in J may be either plus or minus 1 or 0. But 0 to 0 transition is not allowed. In case of L, when the electron is a higher energy level and if it jumps to the lower energy level, the change in its L value is always plus or minus 1. If it is 0, it is not allowed. So, whenever the electron gets transition from one energy level to another energy level, the changes in the L value and the J value should satisfy the condition such that delta L is equal to plus or minus 1 and delta J is equal to plus or minus 1 or 0. But this 0 to 0 transition is restricted. Also, the change in S is always 0. Also, the change in S, that is delta S always 0. That means if one energy level, the electron is in clockwise direction, whenever it takes transition to the lower energy level, there also it must have the clockwise direction only. The direction change is not permitted. The direction of rotation change is not permitted. So that is delta S is equal to 0. That means same direction of rotation is only permitted. These three are called as selection rules. The purpose of the selection rules is used to understand why only selected number of lines are appeared in the spectrum, because only selected transitions are permitted, so we are getting only selected lines. Similarly, now we are going to another topic, that is intensity rules. Here we are in this heading, we are discussing the cause for different intensities of the spectral lines in a spectrum. In VIBGYOR, almost all the 7 colors are not having equal intensities. With the green, red and orange, they are somehow blue also, are having more intensity when compared with violet color. So what is the cause for this variation of intensity? To explain the variation in intensity, there are some conditions are observed. That is, delta, the -1 to -1 will give most intense line. -1 to -1 means if delta L is equal to -1, if it during the transition, the change in the state of the electron gives such that delta J is equal to -1, then we will get most intense line. -1 to -1 will get most intense line. We will get most intense line, or delta L is equal to -1 and delta J is equal to 0, less intense line. And then +1 to +1 weaker line. If delta L is equal to +1 and delta J is equal to +1, we get weaker line. Delta J is equal to +1, we get weaker line. Similarly, delta L is equal to +1 and delta J is equal to 0. Here also we will get weaker line. But if delta 1 is delta -1 to +1 or +1 to -1, delta L is equal to -1 and delta J is equal to +1. Similarly, delta L is equal to +1 and delta J is equal to -1. These two are not allowed. That means if the during the transition of the electron from higher energy level to lower energy level, if it undergoes a change in its quantum state such that delta L is equal to -1 and delta J is equal to -1, that means -1 to -1 we will get most intense line. Similarly, -1 to 0 less intense line, or +1 to +1 weaker line, +1 to 0 also weaker line. Opposite sign is not allowed. That means -1 to +1 or +1 to -1 are not allowed. In this way, the intensity of the transition in such that depends upon the change in L value and J value. The change in L value and J value as shown in the on the notice board. Sorry, as shown on the board. So these are all the intensity rules. The advantage of this is we are successfully explained the reason for different intensities with the help of intensity rules, and also the reason for the definite number of spectral lines with the help of selection rules. So in this unit, the vector atom model successfully explained all drawbacks of Bohr and Sommerfeld models. The vector atom model successfully explained all drawbacks. That means Bohr model failed to explain the spectrum of complex atoms, and similarly the Bohr model failed to explain Stark effect and Raman effect. For all those drawbacks, they were overcome by this vector atom model, because in case of Raman effect is nothing but the splitting of spectral lines when the atom is placed and when the light source is placed in a magnetic field. What happens when the source is placed in magnetic field? When the source is placed in a magnetic field, then the orbit of the electrons gets restructured. That means they suffer reorientation. That means their energy levels were affected. That is the reason why the spectral line, that is the reason for the splitting up of spectral lines. The same is applicable for Stark effect. In case of Stark effect also, in the presence of electric field, the spectral lines are split up into two lines. The reason is the same as we explained for the Raman effect. So these are similarly for the limited number of spectral lines, selection rules. The intensity variations for intensity rules. So here once if you recall all these topics, the first atomic model, not the first model, in Bohr atomic model, it is the angular momentum of the electron when it is revolving in an orbit is quantized such that MVR is equal to NH by 2 pi. This is the most important thing. In almost all models, the basic principle is like this. It is the angular momentum of the electron is quantized such that MVR is equal to NH by 2 pi. But in case of Sommerfeld model, there are two momenta, one radial angular momentum and the other one is azimuthal angular momentum. These two are quantized as they are equal to nr into h by 2 pi and n phi into h by 2 pi. The azimuthal quantum number describes the shape of the orbit, but the orientations in the Sommerfeld model, the electron possesses only 2 degrees of freedom, but actually the electron is moving around the nucleus in space, so its degrees of freedom is 3. So in order to consider the third degree, we have to quantize the orientation of the orbit about an external field which does not affect the orbit of the electron. So the orientations are also limited because of the quantization condition. So in this way, our vector atom model is helpful for us to study and understand the spectrum or the spectrum of almost all molecules or atoms. In the next class, we are going to discuss about Raman effect. Thank you. Ini